Work. From physics, we know that work is equal to force times distance. That is a particular amount of force over a particular distance. If F is measured in newtons and distance d is measured in meters, then the units for work is a Newton meter, which is also called a joule. If the force is measured in pounds and the distance is measured in feet, then the unit for work is a foot-pound. And a foot-pound is about equal to 1.36 joules. This is not worth remembering, but it's just a nice comparison mechanism. Let's look at the first example. And this is a simple example where calculus is not needed. It says how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. And you'll notice it does say use the fact that acceleration due to gravity is 9.8 meters per second squared. So why do they tell you this? Well, because 1.2 kilograms is a mass, not a force. So we need to remember that force is equal to mass times acceleration. And in this case, it's mass times g, where g is equal to gravity. And that is going to be 1.2 kilograms multiplied by 9.8 meters per second squared. And when we multiply these together, we're going to get a Newton. And the total here is 11.76. And this would be kilograms meters per second squared, or we can simply say 11.76 newtons. Now we know the distance is 0.7 meters, and so the total amount of work done here, which we know is force times distance, is 11.76 newtons multiplied by 0.7 meters. And this gives a total of 8.232 Newton meters, or we can simply say 8.232 joules. For part B, it's very much the same thing. How much work is done in lifting a 20-pound weight 6 feet off the ground? Now, in this case, force is given 20 pounds, so pounds is a force. You do not have to multiply by acceleration due to gravity. It's already in the units. And the distance here is 6 feet. And so the total amount of work done here we know is force times distance, which is 20 pounds multiplied by 6 feet. And 6 times 20 is 120. And the units here are foot-pounds. And so these two examples are just to serve as really basic examples where calculus is not needed. Now, why is calculus not needed? Well, it's mostly because as you lift the object, let's say in the case of the 20-pound weight here, the weight of that object is not changing as you're lifting. So the force you need to apply to lift it is the same for the whole distance. So it's when that force starts changing as you're moving the object, that is when we need calculus to help us compute the values. So what if the force is not constant? Let's assume that we are moving an object from this point here, which we will call A, to this point over here, which we will call B. And as we move that object, the force needed at any particular moment here, let's say at any particular moment x, the force is going to be F of x. And assuming that this force is changing throughout here, we can approximate the work done by breaking this down into subintervals. Now, this should sound very familiar to you, but basically what I'm going to have here is the first subinterval is going to end with x1, the second one is going to end with x2, x3, x4, etc. And so somewhere in the middle we have xi, And the basic idea is that when you move this object, or when you're applying this force to move a particular object, the different amount of force you're going to have to apply here compared to here is very small. So although the difference between the beginning and the end might be very large, the difference between two numbers that are closer together is going to be relatively small. So what I can do here is I can pick an x value, this one we'll call x1 star, and we're going to say the force that we need to apply is approximately f of x1 star on this entire interval here. And then I do the same thing for the second interval. I'm going to pick a value, we'll call it x2 star, and the force applied here is going to be f of x2 star on that entire interval. So on each of those intervals there, we are going to take the amount of force that we need to apply, which on the first interval is f of x1 star, and we're going to multiply that by the distance that that particular force is applied, which is only from here to here. And that distance, of course, is what we know to be delta x. So that's the total amount of work done on the first interval. On the second interval, it's the same idea. F of x2 star will be the force multiplied by the distance, which is delta x, etc. So if we keep on doing this all the way until the end, in our final interval here, this will be xn minus 1, and b will be xn. And so if we pick some random value there, we'll call that xn star. The force applied there will be f of xn star, and we're going to multiply that by delta x. And so when you do this, you get the summation I equals 1 to n f of xi star times delta x. And this will be the approximate amount of work done. But then we can make that estimate better. In fact, we can make it precise by taking that sum there and taking the limit as n goes to infinity. When you do that, you get the exact value for work. And of course, we know that when you take the limit as n goes to infinity of a Riemann sum, we know that that gives us a definite integral. So long story short, the way you get the work is by integrating the force function f of x with respect to x from x equals a to x equals b. Now, the hardest part about this is knowing the force function, right? So if the force required is changing, how do you figure out what it is at any particular moment x? So that's really the challenging part for most of these work problems. So in this example, we have everything set up very nicely for us. It says, when a particle is located a distance of x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? So we know that our force function f of x is x squared plus 2x. And so therefore the work to be done on this object will be the integral of that force function with respect to x, and in this case from x equals 1 to x equals 3. So when we take the antiderivative, we get x cubed over 3 plus x squared. Now we're going to use the fundamental theorem of calculus, plugging in x equals 3 minus plugging in x equals 1. And this gives us 9 plus 9 minus 1/3 minus 1, which is going to be 16 and 2/3. And 16 and 2/3 is the same as 50 over 3, and this will be measured in foot-pounds. Now let's take a look at work involving springs. So when you have an object connected to a spring, moving the object in either direction, either compressing the spring or stretching the spring, requires work. Now, it is true that the force required to move an object attached to a spring, X units beyond its natural length, that force is equal to K times X, where K is the spring constant. So the value of K determines how stiff the spring is. So one of the things you'll need to do in computing work involving springs is you'll have to find the spring constant if it is not given to you. So here I have a couple of simple examples of finding a spring constant when you're given certain pieces of information about a spring. So in the first one here, we want to find the spring constant if 10 pounds of force is required to keep a spring stretched 4 inches beyond its natural length. Okay, so the force required is 10 pounds, and the distance that it is being stretched beyond its natural length is 4 inches. Now, typically we don't work with inches when dealing with pounds. We typically want to work with feet. So we're going to remember that 4 inches can be changed into feet by multiplying by 1 foot for every 12 inches. And if you do the conversion factor on this, you get 1/3 of a foot. So now, since we know the force is equal to K times X, we can say 10 pounds is equal to K times 1/3 of a foot. And then what we're going to do here is we're going to multiply by 3 to both sides, and that will cancel out the 1/3 there. And that's going to give us K is equal to 30. And just for clarity, it's going to be pounds per feet. And that is the spring constant for this particular spring. Now, in the next example, it says, find the spring constant if 3 foot-pounds of work is required to stretch a spring from its natural length to 6 inches beyond its natural length. Okay, so this is a completely different problem because I'm not saying that there's a force required like I did in the previous example. I'm now saying that there is an amount of work required to stretch the spring. So we know that work is equal to the integral from A to B of your force function, f of x dx. Well, in this case, your force function is K times X because we do not know the spring constant. And it's being stretched from its natural length, so that would be A equals 0, to 6 inches beyond its natural length. And we're going to change 6 inches to 1/2 of a foot. So now we know that the work done is the integral from 0 to 1/2 of kx dx. And this is going to be kx squared divided by 2 from 0 to 1/2. And this is going to be k times 1/2 squared divided by 2 minus k times 0 squared divided by 2, which of course is 0 there. And we end up getting k times 1/4 divided by 2, which is 1/8 k. So the work done is 1/8 k. Now we don't know the spring constant, but we do know the work done is 3 foot-pounds. So we know that whatever this work is that we got in the end here, it has to be equal to 3 foot-pounds. So then to solve for k, if 1/8 k is equal to 3, I simply need to multiply both sides by 8, and that will give us k is equal to 24, and this will be pounds per feet. So there are 2 ways that you can calculate the spring constant. One way is when they give you information about the force required to hold the spring, and the other one is when they give you information about the work required to stretch a spring. So now let's take a look at the following example. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is being done stretching it from 15 centimeters to 18 centimeters? Okay, So first of all, we need to take note of the fact that the natural length of this spring is 10 centimeters. And I'm going to say that 10 centimeters is 0.1 meters. And this is because you can do a conversion factor. 1 meter has 100 centimeters in it, and that is going to be 0.1. Okay? So the natural length is 0.1 meters. And you can actually draw a little diagram here. Let's say that this distance from here to here is 0.1 meters. And up above there, I'll remind you that that is the same as 10 centimeters. And it says that a force of 40 newtons is required to hold it at a length of 15 centimeters. Okay, overall length of 15 centimeters. So we are holding it this distance, which is 15 centimeters. So the amount that it has been stretched beyond its natural length is 5 centimeters, or if I say that down here, that would be 0.05 meters. All right? So we know that the force is equal to K times X. And in this case, we know the force is 40 newtons. K is what we do not know, but the distance that it has been held beyond its natural length is 0.05 meters. And so if we just simply divide both sides by 0.05 meters, we will get our value for K. And in this case, 40 divided by 0.05 is 800, and that will be newtons per meter. Okay, so that is the value of the spring constant. And what that means now is for this particular spring, we can say the force function is 800 times X. So all I'm doing there is taking this value of K and plugging it in. And by the way, you'll notice that sometimes I call the force capital F, and sometimes I call it f of x. It really doesn't matter what you call it, but once I put it into the function format, I do like to call it f of x at that point. So now it says how much work is done in stretching the spring from 15 centimeters to 18 centimeters. So let's think about this for a minute. So here we are at 15 centimeters here. We're going to stretch it to 18 centimeters. So this point is 18 centimeters. And 18 centimeters is 8 centimeters beyond its natural length. Keep in mind, the natural length is 10 centimeters. So when we're at 18, we have gone 8 centimeters beyond its natural length. And so the distance from here to here is 0.08 meters. Okay, same as 8 centimeters. So when I go to calculate the work being done, I know that work is equal to the integral of the force function, which is 800x dx. But here's the deal. We are going from 15 centimeters to 18 centimeters. But two things. We have to compare that to the natural length. So the natural length was 10 centimeters. When we're at 15 centimeters, we are 0.05 meters beyond the natural length. And when we're at 18 centimeters, we are 0.08 meters beyond the natural length. And so it's very important that you use meters for your limits and not centimeters. Now, doing the rest is relatively simple. The antiderivative of x is x squared over 2. So we end up getting antiderivative of 400 x squared. And we are going to go from 0.05 to 0.08. And so we have 400 times 0.08 quantity squared minus 400 times 0.05 quantity squared. And when you do the math here, you get 7.44, and this will be joules. So we can say 7.44 J for joules. In the next example, we have a 200-pound cable that is 100 feet long and hangs vertically from the top of a tall building. how much work is required to lift the cable to the top of the building? Okay, so I have a simple diagram here. We have a building with an unspecified height, but it is taller than 100 feet. And we have the cable hanging down from the top of the building. Now, you'll notice that the cable hanging down here, I have not put it at 100 feet. So what I'm doing here is I'm showing you that this is what the cable looks like in the process of lifting it up. So at some point, we have X feet of cable hanging down, and we are going to hoist that up continuously until all of it is up to the top. So what we need to do is figure out, at this particular moment, when you have X feet of cable hanging down, what is the force function there? Well, if we have X feet of cable, we're going to multiply that by 200 pounds divided by 100 feet, because we know that the total amount of cable is 200 pounds, but there is 100 feet of cable. And basically, this is 2 pounds per foot, right? 200 divided by 100 is 2. And so the cable weighs 2 pounds per foot. So if we have X feet of cable, we multiply that by 2 pounds per foot, and we get 2x pounds. Okay, so when the cable is hanging down there, when you have X feet of it hanging down there, you have 2 times X pounds of cable. Now the question is, what is the distance that it is going to be hoisted? Well, it's only going to be lifted a very small distance, call that delta X. Once you've lifted a small distance, there is now a little bit less cable hanging down, and the force will change. So the distance that it's going to be lifted is delta X. And so the work done is going to be the integral of 2x times dx, right? dx is basically delta x. And we're going to do this from 0 to 100 because you're starting with 100 total feet of cable. So if we do the math here, we get x squared from 0 to 100, which ends up just being 100 squared, which is 10,000. And in this case, we will have foot-pounds. So 10,000 foot-pounds of work to be done lifting the cable up to the top of the building. And this is lifting all 100 feet of it. In part B, we want to know how much work is required to pull up only 20 feet of the cable. So for this, I've modified the diagram just a little bit. You'll notice that we have 100 down here at the bottom and 80 here. Now the reason I put 80 is because when you lift 20 feet of the cable will now be hanging down at 80 feet. So again, X is some value between 80 and 100. That is how much cable we have hanging down. So the weight of that cable, or the force of that cable, F, is going to be 2 pounds per feet multiplied by X feet. And again, this is 2X pounds. Now the distance is once again delta X. So the work done here is going to be the integral. Now here's the interesting part. We're going to integrate only between 80 and 100. And so we're going to have the integral from 80 to 100 of 2x dx, which is x squared from 80 to 100, which is 100 squared minus 80 squared, which is 10,000 minus 6,400. And when you do the math on that, you get 3,600. And again, these will be measured in foot-pounds. Now, another thing I should say is that for work problems, there's often multiple different ways to look at a particular problem. And so when you do your own research to look for methods to solve these problems, you might see things that look slightly different from what is done here. As long as you can justify what is your force and what is your distance, again, there's multiple ways to approach a lot of these problems. In our final example, we have a tank in the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. So you can see that cone-shaped tank here. The radius at the top of the tank is 4 meters, and the height of the tank here is 10 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. So we are going to be pumping the water up and over. And the density of water is 1,000 kilograms per cubic meter. All right, so we have a nice diagram here. What we're going to do is look at a little slice of water somewhere in the middle, and we're going to find out how much work is required to take that slice of water out over the top. So how big is this slice of water? It's a little disc, you should notice there, and that disc has a particular radius r, and that radius r is going to coincide with the height of the water level there. We'll call that h. So if we define the distance from the top of the tank down to this slice of water, if we define that to be x, then the distance from here to here will be 10 minus x, because again, the height is 10. So we can now set up a proportion to solve for the radius here. So we know that the radius r compared to the height h will be equal to the base radius, which is 4, compared to the total height, which is 10. And so this says that r is going to be 4 divided by 10 is the same as 2/5, and then multiplied by h. But again, we know that this value h right here is this distance, and this distance we said was 10 minus x. So the radius is going to be 2/5 times 10 minus x. Now the reason we need to know that is because we're trying to figure out how much this little slice of water weighs, right? So when we do that, we're going to need the volume of that little slice of water. And to get that, we're going to need the radius of the circle. So we now know the radius is 2/5 times 10 minus x. To get the volume, we're going to take pi multiplied by that radius squared, and then multiplied by the thickness of that chunk of water, which is delta x. And so what we get there is 4 over 25 pi times 10 minus x quantity to the second power, and the delta x is going to become a dx when we do the integral. Okay, so that's the volume. Now, how much does that little piece of water weigh? Well, we know that water weighs 1,000 kilograms per cubic meter. So this right here is cubic meters. So the force, the amount that it weighs, is going to be that volume multiplied by 1,000 kilograms per cubic meter multiplied by 9.8 meters per second squared, because remember, we have to express this as a force, and the 1,000 kilograms is a mass, not a force. So we have to remember to multiply by 9.8. So now let's go ahead and multiply all these numbers together. So 4 over 25 times 1,000 times 9.8 is 1,568, and then we still have the pi there, and we still have 10 minus x. Oh, that should be quantity squared. Let's fix that. There we go. And then dx, and again, remember this was meters cubed here, so the meters cubed cancel, and we get kilograms meters per second squared, and those are newtons. So we now have the force. Now, what distance does that force have to work upon? Well, to get this chunk of water pumped over the top of the tank, it has to travel a distance of x units. So we're going to say that our distance is x meters. And so then the work done is going to be the integral of your force, 1,568 pi, times 10 minus x quantity squared, times dx, and then don't forget we're multiplying that by the distance x, and we're going to integrate this from 0, excuse me, not 0, we're going to integrate this from 2 to 10. Now, why 2 to 10? Well, again, you only have water up to 8 meters, okay? So when it's filled up here at the beginning, this is the 8-meter mark, all right? But we're calling this distance from here to here, we're calling that x. So that means this is 0 and this is 10. So if the water is filled up at the 8-meter height level, that corresponds to x equals 2 in our coordinate system, okay? Now that's because we're calling the top of the tank 0 so that the distance that it has to travel is x. So we got to make sure that we have the right units here. Now from here, we just go ahead and do the integration and get the answer. So let's go ahead and factor out 1,568 pi from our integral. And let's multiply this out. This is going to end up being x squared minus 20x plus 100. And then we have to multiply that by x. So that's going to be 1,568 pi integral of x cubed minus 20x squared plus 100x. Now let's go ahead and do the integration. Let's bring this up to the top here. We have 1,568 pi. Now the antiderivative of x cubed is x to the 4th divided by 4. Antiderivative of negative 20x squared is going to be negative 20x cubed divided by 3. And then finally, the antiderivative of 100x is 100x squared divided by 2, which is 50x squared. And we go from 2 to 10. So let's go ahead and plug in 10. 10 to the 4th power is 10,000. Divided by 4 is 2,500. Minus 10 to the 3rd power is 1,000 times 20 is 2,000. 20,000 divided by 3. Plus, when we plug in 10 here, we get 100 times 50 is 5,000. Minus, now let's go ahead and plug in 2. 2 to the 4th power is 16. 16 divided by 4 is 4. Minus, when we plug 2 into here, we get 2 cubed is 8 times 20 is 160 over 3. And when we plug 2 into here, 2 squared is 4 times 50 is 200. Now, I'm going to go ahead and use a calculator to combine all these numbers together. Of course, we could do it by hand, but in the interest of time, let's go ahead and just plug that in. And when doing so, we get 2,048 over 3. And now I'm just going to plug all of this into a calculator. So if we take that fraction and we multiply it by 1,568 pi, we end up getting 3,362,828 joules. And this is an approximate answer. And that concludes this video lesson.